Okay, so generative models. I focus here on images. Tomorrow we will see how to deal with text from Raphael. They're really popular right now, as you might have seen in the news. There's also a lot of potential for misuse, but we will not discuss this here. It's a very important topic nonetheless. Few disclaimers. I will do like a very short introduction. Is an overview of some of the architectures, some older ones that are a bit simpler to understand. There is a lot of maths involved, and I'm sorry for the more maths-inclined people in the audience, but we will not go through all the maths because we don't have enough time. And yeah, many architectures are really quite complex, especially the latest one where I have only a few slides on them or just pretty pictures that they generate. But they really deserve their own lecture on them. So what we are trying to do is mainly to build some intuition and learn the jargon and how you can use this model. And then at the end, I have a slide with all the references. So if you want to go and read the original papers and learn more about them, there are also plenty of tutorials online and tutorials on the PyTorch website that you can look into in order to understand them better. So what we've done so far, essentially, is to estimate this probability of y given x. So we have an input, for example, an image, x, and then we want to define the probability of different classes for classification. So this is what we have been doing up to now. Generative models, essentially what you want to do is to estimate the probability distribution of your input. And the reason is that if you can estimate this probability, that means that if X is an image of your data set, your training data set, and you will have a high probability for that image, you can actually sample this distribution to generate new images. And then there are also conditional generative models that we will not see, but they're really important right now, where you give some condition, like a prompt, a text prompt, for example, and then you can generate an image that is described by this text prompt. And yeah, one example that can be used for generation of images is what is called an autoencoder. It's not a very good model for generating images, and we will see why in a bit. But essentially, you start with your input x. Think about x as images, but this is a general architecture that you can apply to other kind of data. Then you have an encoder that essentially reduces the dimensionality of your input into a linear vector, which is called the latent space vector. So you have essentially a lower dimensional representation of your input, and then you can also train a decoder neural network that takes this latent vector and generates a new instance of with the same size of your input image. And if you train it, the hope is that given z, you can actually get a pretty good approximation of the input image. And this is called the autoencoder because essentially you encode and then decode into a new image. But the way you train it is essentially, and this is where the autoencoder name comes from, the loss function is essentially the difference between the input image and the output image, which is you consider as the generated image. And yeah, essentially, the autoencoder is a neural network that is trained to copy its input to its output. So you start with an image, and then you have an output image. By the loss function, you are forcing them to be the same. But it cannot just like do the copy straightforwardly because you're reducing the dimensionality with the encoder. And so this is a lower dimensional space. And so the model has to learn some good lower dimensional representation from which can generate new images. And if you are familiar with principal component analysis, a linear autoencoder with a single layer and no activation functions is actually performing PCA. So it's a dimensionality reduction technique. And essentially, yeah, you go into a lower dimensional space, and then this decoder is essentially learning the inverse of the encoder transformation. But yeah, you're not, since you can represent the encoder and the decoder as neural networks, you're not you're not bound to use a single linear layer and perform PCA, but you can use a feed-forward neural network, for example, or a convolutional neural network as your encoder and decoder. And so you can get pretty crazy about the architectures and try to come up with latent representations that are meaningful and good for this task of essentially given an image, recreate the same image. So one thing to discuss is, well, the encoder is somewhat trivial in the sense that we have seen already the CNN architectures that go from like an image of size, for example, 28 by 28, into a lower dimensional representation that would be essentially the output of your linear layers. But what we are missing is essentially the reverse. Essentially, we have to reverse what the convolution do. For feed-forward neural network, this is quite simple because you can just have linearize your image, and then you have, for example, 256 input, and then 10 outputs. And then in the decoder, you can have a neuronal network made of linear layers that goes from an input of 10 to an input of to an output of 256, for example. So with linear layers, this is quite simple, but with CNNs is a bit more difficult because you essentially need to define something that gives you a bigger image and upsample the image. So the question is how to go from a small latent space in a single vector back into the pixel space of the images. And as I just mentioned, the linear layers are easy because you have, you just transpose the weight matrix essentially, but with CNN it's a bit more complicated. There are different ways that you can do that. There are essentially variation of the maximum pooling, but is essentially unpooling. So for example, nearest neighbor, it means that when you increase the size of your image, you just take the one pixel that you're trying to resize. Maybe you'd make 1 pixel into 4, and you just take the same value for all the 4 pixels when you go to bigger images. Unpooling is really simple. Then you can also do interpolation. So for example, if you go from 1 pixel to 4, how do you fill the 3 pixel that you added? You can do interpolation with the next pixel up. And then the final one that is usually used is what is called transpose convolution. And in essence, transpose convolution is the same as a convolution, but on dilated images. So this is actually also a visualization of what the dilation parameter does in the convolution. But essentially, you take a 3x3 image, you dilate it, and you add essentially 0 between the pixels, and then you apply a convolution to this dilated image. And so the output you see that is, if you do this convolution, is bigger than the input. And so you can use this transpose to the convolutions to actually upsample. It's essentially like the inverse of structurally is the inverse of the convolution operation. And is a big pain to figure out the dimension, padding, and stuff like that. So this time in the notebooks, I've been nice, and I created the, I did the architecture, so you don't have to actually calculate the dimensions this time. The problems with this kind of models is that, well, I mean, once your model is trained, you have essentially a decoder that, given a sample in the latent space, can create an image. The problem is that there is no structure in the latent space because it is not been constrained in any way. So yeah, essentially for generating images from an autoencoder, we can sample points in latent space and use the decoder to convert them back to pixel space. But different classes have different distribution in latent spaces. So if you are encoding a lot of numbers from the MNIST dataset, for example, maybe the ones have different distributions in latent space than the twos, and so on and so forth, because no structure was imposed in the model. You're just trying to recreate the input when you train. It's unclear how to sample it, because like what distribution the latent space has, you don't know. So you don't know how to actually generate the Z that then you can decode into images. And then a related problem is that a random point in latent space does not always decode into a meaningful image, because sometimes the model just essentially put all the similar images and encodes them into nearby pixels in latent space, but then you have parts of your latent space, which is the latent space where the Z vector lives, that are not decodable into anything because they've not been learned. However, there is one quite interesting application of autoencoders, and they can be used for denoising images, because essentially you're trying to copy an input to an output. And if you have noisy images, here I took the MNIST dataset and I added some random noise to it. You can actually input this, the noisy image here, and then, well, you will get an output during training, but then you can compute the loss function between the output and not the input, but the image that was not noisy. So you don't use the noisy image, but you use the original image before noising it. And by doing that, by comparing the output image to the denoise one, you're essentially forcing this model to learn how to denoise the image. And the way it works is essentially that since you have an information bottleneck, because the size of the latent space vector is smaller, the model is forced to essentially only keep the features that represent the original image and essentially discard all the noise. Yeah, if you finish quickly the exercise, you can try to implement this. And then there is a completely different beast, and this is a probabilistic model and tries to solve the problems of autoencoders, and it's called variational autoencoder. It seems similar in architecture, but it's completely different things, and there is a lot of probability theory behind it, but as I mentioned, we will not go into the details. But essentially, what you do in this case, instead of predicting directly from the decoder a latent space vector, you predict a probability distribution. So your encoder will give you a mean and a variance. You assume that this distribution is a Gaussian distribution, and then your Z is a sample of this Gaussian distribution with the mean and the variance that are produced by the encoder. And so the encoder produced the mean and the variance of the Gaussian distribution. Well, in practice, you produce log of sigma squared because the variance is always positive. And so log of sigma, you consider the output of your model as log of sigma squared, because the output of, for example, a linear layer can also be negative. And then the decoder produces similar images to similar points in later space, because essentially when you decode during training, by encoding the same image, you will get a slightly different representation in latent space, because you're sampling from a distribution. So the Z will be, well, around the mean, but it will be slightly different each time. And this means that the decoder has to decode similar latent space vector into similar images. And in this way, you give some structure to the latent space. We can probably skip this one, but essentially there is this is a way, a measure for measuring how two probability distributions are similar. Is always positive and is 0 only if the two probability distribution P and Q are the same, and it's called the KL divergence, very famous metric for this kind of models. We can skip the details, and again, we skip the whole derivation that is on the paper of what the loss function for the variational autoencoder should look like, but essentially is made up of two components. The first component is the reconstruction loss, which is exactly the same that we had for the autoencoder. So this one is the square difference between the input and the output. But then there is also an additional component, which is what gives the structure to the latent space, and is essentially this KL divergence loss. And since you're working with Gaussian distribution, so this is essentially the Gaussian that given xi gives you zi, so essentially represent the the encoder, because you given x, you produce z. So this is this probability distribution here. And then this is the probability distribution that you decide, this is a constraint that you put for the latent space, so you want that it produces a Gaussian distribution. And if you do all the calculations, very lengthy derivation, probability theorem, blah, 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 but at the end you get this loss function here that depends on the predicted variance and the predicted mean. So the loss function only depends on what comes out of here.
Question, in that picture that you've got on screen there, the mean and standard deviation, this is an n-dimensional Gaussian where the dimensions match the size of z, yeah?
Yeah, exactly.
Okay.
And then you consider the covariance matrix to be diagonal. And this you produce the diagonal of the covariance matrix.
I'll just take your word for it.
I mean, this is how you build the model.
Okay.
This is a constraint you put. It's a multidimensional Gaussian distribution, but instead of producing a covariance matrix, you produce a diagonal covariance matrix, so just the vector of variances. Does it reply to your question? Or? So in terms of like neural network, you will have like a common part of the encoder that could be, for example, a feed-forward neural network that gets you down to, let's say that you want a latent space dimension of 10. Then you have a common part of the encoder that produces a lower dimensional, for example, the output is of size 100. And then you will have one additional linear layer that produces the mean, and is a linear layer from 100 to 10. And then you have another linear layer that takes the same output and then produces the variance, and is again a linear layer that goes from 100 to 10. And then you have the mean and the variance, and you can sample from that distribution.
My conception is missing, because after the encoding stage, you effectively only have a single vector.
No,
Because so this is the mean of a single item, because you've reduced your dimension of your input from, let's say, lots to down to a dimension of 100.
Yeah.
Now you've just got 100 numbers there, which each are in their own dimension. They all represent one dimension of the image features or whatever.
Yeah.
So what are you taking the mean and the standard deviation of?
Another linear layer that actually, maybe a drawing is better at this point. But you can have essentially, let's say you have like a feed-forward neural network, and you want to go down to just 2 numbers. So this is a feed-forward neural network. You do the usual blah, 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 okay? And then this is essentially the end of the blue encoder. And then now what you can do is that you attach 2 separate neural networks. Let's say that the size of the latent space dimension is 2. So you can have something, a linear layer that produces 2 numbers, and this is your mean. Yeah? And then for the variance, you can have another linear layer that takes exactly the same inputs and is also of size 2. And this you interpret it as your variance.
In this case, the Z is just dimensionality 2 then?
Yes, exactly.
Fine.
Yeah. Does this clarify some things? Yeah. So this is a bit more complicated as a model because you have essentially 2 outputs instead of just the one that we had before. Okay. Then there is a big problem with this model for backpropagation, because essentially you're producing a mean and a variance with your encoder, but then you have a sampling of a random variable from the normal distribution with this mean and this variance. And this is problematic for backpropagation because you cannot backpropagate through a sampling layer. And so what people came up with is to do a reparametrization trick and use the properties of a Gaussian distribution. If you want to have Z that is distributed with a mean mu and a variance standard deviation sigma, you can actually sample from a normal standard distribution and then just multiply by the standard deviation and sum the mean, and then you get that Z is distributed according to this Gaussian distribution. And the reason why you do that is essentially this is the computational graph of your operations before the reparametrization trick. So you have mu, sigma, and then you produce Z with a sampling layer, and you cannot backpropagate through this sampling layer. And so the reparametrization trick, what it does is that it essentially moves the sampling layer that now uses a standard normal distribution outside of the paths in the computational graph on which you want to compute the gradients. Because the mu is essentially the output of your encoder, so you want to propagate all the gradients through your neural network. And so you do this reparametrization trick to be able to do the backpropagation. Do you have any question on this one? No? Okay. Then to give some examples on how you can use this variational autoencoder, for example, this very nice example from computational chemistry and drug discovery. But essentially, you can imagine an encoder that takes a molecule. Then you have a neural network that encodes it into, here is represented as a 2-dimensional latent space. This is a continuous space of essentially numbers that represent encoded molecules. And then you can have a decoder neural network that gives you a molecule as output from each point of the latent space. And what's quite interesting is that you can also apply another neural network in latent space. So you take the Z numbers that is here, and then you produce, for example, you do some property prediction of the molecule that you encoded. So for example, it could be like lipophilicity or some property of the molecule. And what's quite interesting, because you have back propagation, you can actually compute, well, you have this function is a neural network, but you can compute it. You have the latent space vector Z, and the output is your property, f of z. But since it's a neural network, you can use backpropagation to compute the gradients of this property function, and actually you can optimize this function in latent space to optimize some of the properties. So for example, here maybe you want to maximize let's say that this property is the solubility of a molecule. You start with your input, encode it into the latent space. You would be, for example, here. And then you try to optimize the solubility of this molecule in latent space by doing optimization on this function, because you have the gradients. You can obtain them by backpropagation. And then once you get a point in latent space where this property is optimized, you can use the decoder to essentially generate the corresponding molecule. So this is a very interesting application of this kind of models. Do you have any question on this one? Okay. Then another class of interesting models for image generation is called generative adversarial models. And this one, they always have this random noise that you start with and a generator that tries to take this noise and transform it into an image. But in this case, you don't have any encoder, but you have a discriminator network. And this discriminator network is a classification network, exactly the same that we have seen in the exercises. But instead of classifying an image as depending on the content of the image, essentially it tries to classify real and fake images. So it tries to figure out if an image comes from the data set or if it's been generated by the generator. And essentially you put those two models one against the other. And so the discriminator will try to guess if the input you pass it is a real image or a fake image. Well, not to guess, but to learn, to classify it. And the generator will try to fool the discriminator. And during training, the generator will become better and better at generating new images that looks like your input. And so at the end of the training, hopefully, if everything goes well, the discriminator will output essentially 0.5 and 0.5, cannot distinguish anymore the images generated by the generator or the images on the of the original data set. So the training goes into two steps. Essentially, at every epoch or for every batch, you do a step on the discriminator and a step on the generator. So you will have two different neural networks, one that is upsampling from Z to X, and one that is essentially the standard convolutional neural network for classification that gives you real and fake images. So you will have also two optimizer, one for the discriminator and one for the generator. So it's a bit more complex and involved to what we have seen so far. But the concept is exactly the same. You can compute the gradients by backpropagation, then take the optimizer step to change the parameters of each model. And for training the discriminator, what you do is you get a batch of real images from the training set, and you label them as 1. and one is what you consider as real images. And then you also get a batch of fake images from the generator. So you will have essentially double the batch size, but half of the batch will be real images and half of the batch would be fake images. You combine the two batches into a single one so that the final batch will contain some fake images and some real images, and then you train the discriminator one step with binary cross-entropy loss. This is the cross-entropy loss for a binary classification problem because we only have 2 classes in this case, real and fake, instead of the 10 classes, for example, we are used to. But it is essentially the same. It is the same loss function because we are doing a classification, and the classification is real versus fake images. Yeah.
And why one step? Why one step?
Because you have to train them at the same time.
But then those would depend also on your how you optimize. What kind of step you take?
Yeah, I mean, one step. This is one step of the training loop. But we are missing the second part, that is the generator. So you do in one training loop, you do one step on generator and one step on the discriminator, and then you loop. Yes. For step, I mean an update of the weights. But then you keep looping. Is it clear? Or?
No, it's clear. Just
So you do many of these steps, but first you do one step, then you do the generator one step, and then you go back and loop.
maybe it's unclear why should be only one step, because it depends what kind of weight you do, right? Like what descent you use, which parameter you use.
Yeah, but it's not one step in general. It's just that you do by one step, what I mean is that you call optimizer.step. So you do one update of the weights for the discriminator, then you do one update of the weights for the generator, and then you loop back and get another batch of images. So essentially it's the same as we were using before. Before we were doing one step in the training loop. You do optimizer step for one batch. But here, before looping, you also have to update the generator. Is it clearer? Yeah, okay. So you do essentially one step. This is essentially what I'm describing here is the innermost part of your training loop. So it's inside 4 epochs and then 4 images in train loader. And then you do one step. Okay. And then for the generator, you have something similar, but you get a batch of fake images from the generator. You don't get real examples this time. And this is a different batch of fake images from the one you have before. You set the labels to 1. And this is the most important trick. Well, this is what makes this model work, is that after you did one step for the generator and you improved the generator for training images, if you remember, I mentioned that label of 1 is real images, and fake 1 as a label of 0. So when you train the discriminator, you use the correct labels. But when you train the generator, you pretend that the generated images are actually real images. So you're trying to fool the discriminator and make him think that the labels, well, I mean, you set the labels to 1, so you make him think that the generated images are real ones. And then because you still pass it through essentially, yeah, you set the label to 1, and then there is a step missing, sorry. You do the prediction of the discriminator, and the discriminator will tell you, well, if it's a real or fake image, and then you train on the binary cross-entropy loss. To understand this a bit better, it's useful to think, to assume that you have a perfect discriminator. So if you have a perfect discriminator, it's very good at discriminating real images from fake images. Okay, is very good. Let's assume that. So what happens if you generate a batch of fake images and then you give a label as they are real? Well, the generator is very good. The discriminator is very good. So it will know that they are fake images and will predict them as fake. But since you put the label as 1, the loss will be very high. Is this clear? Or yeah? Because you're pretending that they're 1. And if your generator is perfect, it will know that they're fake images, but then you're saying, oh, actually, I'm telling you that they're real, and so the loss function, because the labels predicted, essentially the labels predicted by a perfect generator on fake images will be 0. But then you set the labels as 1, and so if you use the cross-entropy loss with labels of 0 and labels of 1, essentially is the maximum, is the highest loss you can get. And then when you do the gradient descent step, you will change the weights of the generator to decrease this loss. And the only way to decrease this loss is generating better images that looks like real images. Because if your generator at the end of the training produces real images, then the discriminator output for fake images that are really good and look like real will be 1. And so at the end of the training, you will have that the loss between the predicted one and the one that you set is essentially 0. And so you're minimizing this loss. Is this clear? Okay. It will be explained, probably it gets a bit clearer on the notebook.
Question.
Yeah.
There's a question here, which is that you've got a discriminator and a generator.
Yeah.
Why don't you just throw away the discriminator? You've already trained a network to recognize cats. Now you want to generate fake images of cats. Just have a network which already knows what cats look like and just train a generator to fool it. Why do you have to train the other side of the network at all, is my question. If you go back like 1 or 2 slides to that image there, you see you've got a generator and a discriminator, and you're training the discriminator, the generator, the discriminator. If you've already got a discriminator which knows what cats look like, then why not just use that?
Yeah, but it doesn't, like, I mean, if you classify, you're probably thinking about the architecture of classifying cats, right? But here the classification is between real and fake images.
Okay.
So at the beginning, the generator will be completely rubbish, but you still have to train a neural network that can
tell the difference between a real cat and a fake cat.
Yeah, real cat and fake cat, essentially. Yeah. But at the end of the training, you actually throw away the discriminator. You don't need it anymore. Then you just use the generator. You sample from the Gaussian distribution, some like a latent space vector Z, pass it through the generator, and then you will have generated images. And you don't care about the discriminator anymore. It's just used for training. Where were we? Yeah, okay. Yeah, essentially, well, can be proved that GANs have a single equilibrium point where the generator produces realistic samples, so the images are really realistic, and the discriminator doesn't know if an image is fake or real anymore. But the problem is that there is no guarantee, mathematical guarantee, that you will ever reach this equilibrium. And then something else that happens quite often is called mode collapse, where, for example, if you think about the MNIST dataset, you have 10 numbers, but sometimes your GAN will just produce zeros or just ones. So it doesn't learn the whole diversity, but it becomes less and less diverse and just produce parts of your dataset. And this during training can actually happen cyclically sometimes. So for a bit of training, you start producing only 0, and then you go on training, and then it starts to change, and then produce only ones, and so on and so forth. Sometimes, because you have these 2 neural networks that are competing one versus each other, you have some instabilities in your training, the training essentially diverges, and it's very sensitive to hyperparameters. A very good example of this is that when I created the notebook, I tried to use like very simple convolutional neural network, like the ones that we have seen before, and the results were okay, but a bit rubbish. And I went back reading the paper, and they have a lot of recommendation of what to use and what not to use, and which, for example, they recommend not to use max pooling layers and stuff like that. And when you implement all these changes on the architecture, well, the images that you get in the notebook are much better of the first version that I was getting. So it's a really challenging thing to train, and this is one of the examples where if you're trying to do something similar, go back to previous paper and previous model and read if they have some recommendations for training. One very interesting thing of GANs, again, you can think about the generator and discriminator very generally, so there are some neural networks, but again, if you're working with images, the most sensible choice is to use convolutional neural networks in the discriminators and also convolutions in the generator, but since you are upsampling, you will use transpose convolutions in the generator. But you can think about other neural network architectures for other tasks, or also like linear layers, but the linear layers don't work that well. And one thing, this is called DC GAN paper, deep convolutional GAN. It means that you use deep convolutional neural network for the discriminator and the generator. But what's quite interesting that they show in the original paper is that the learned representation in latent space are actually quite meaningful. So for example, what they do is that they generate some images, like a bunch of them, and then they selected 3 images of men with glasses. They took the average, they looked at from which points in latent space these images were coming, and then they took the representation in latent space and computed an average. Then they did the same for some men without glasses, and they get an average. So this is what the average decodes to. And then they took some images of women and took the average. And then they took simply a vector sum in latent space. They subtracted men with glasses from men without glasses from men with glasses, and added the latent space representation of women. And if you decode it, you actually get this image of a woman with glasses. So the representation in latent space that this model learn can be meaningful. And also they did, here there are 9 images because they also perturb a bit this vector to make sure that the latent space, like that it was not a fluke, and if they sample a bit to the left or a bit to the right, I think they add some Gaussian noise or something like that on the latent space vector, they can still decode similar representation. So yeah, it's really interesting. And then one model that is very popular at the moment is called the denoising diffusion probabilistic models. I had some slide on it, but I cut it down because it was a bit too much. But essentially is another way of generating images where you have a forward process where you go from an image and you add more and more Gaussian noise to the image with this probability. Essentially, you have a Gaussian probability distribution of going from xt minus 1 to xt, and you essentially noise the image in the forward pass. And what you model tries to learn during training is a very complicated model, so we will not go into details. But essentially, the model tries to learn the denoising of this, the denoising step, so the inverse backward process, the inverse transformation. You can learn it with a very complex neural network, and once you have the training, you can actually start from noise and slowly recover some images. It's a very complicated architecture, so the implementation details are completely outside of the scope of this class. It requires also some knowledge that you will acquire tomorrow, because this architecture uses positional encodings that Raphael will talk about tomorrow, and also attention that will be in tomorrow lessons. So after tomorrow, hopefully you will be able to at least read the implementation and understand the different concepts, but we will not go through it here. I put a link to this website that is actually quite nice, where you can go and can you see? Is it big enough? But essentially, it's a website where they show you the implementation and the theory side by side, and so you can. I mentioned that we were skipping a lot of maths, but essentially you can see what parts of the model correspond to equation that usually you find in the paper. So, for example, here you see that you're generating a vector from a random standard Gaussian distribution, and you see the equivalent PyTorch code to actually do that. So it's quite interesting to look into it. And this is the UNet model. If you click on it, you can see the architecture is quite complex. I think this is the original UNet. You have all the tools to understand it, because it's essentially convolution, ReLU, max pooling, and up convolution are the transpose convolution that I was mentioning. And then here there are some skip connections that we mentioned yesterday, but you can see it's a very complex model, and then requires, this is why we don't go through it, but requires a lot of, it is a very big model, but you can go through it if you want to after tomorrow's lectures, because you will have some more information about what different layers do, if you want to. And by the way, there are also other models on this website that you can look at, and it is a really interesting website to understand a bit the code and the theory together. And finally, as I said, I will finish with the nice images and not too much information, but you can have models that are conditioned on text to generate images. So you pass a text, and here I try to come up with something slightly funny. I don't know if you find it funny, but you pass this text to the model, so a description of the image you want, and then they use this diffusion. This is based on diffusion, but in latent space, so it's even more complicated than the model I showed here. But you can generate pretty nice-looking images. Can
you explain a bit why it's called stable? Or what does the word mean?
I don't know. I have to admit, this one I haven't read the paper yet. I just downloaded the model, and I was surprised how easy it is to use, because it's released open source. You can, I ran this on my workstation. And it took 1 minute to generate these images. So that was pretty good. And you can download the model on GitHub, and then it's a bit convoluted, but then you can download the weights from another website, and if you put it in the right folder and everything, then it took me a while to get it working, but it's just details of where you put the weights and set up your Python environment and stuff like that. I was really impressed that I could get this working quite quickly. What have we missed? A lot. As I mentioned at the beginning, this is just an introduction to give you an overview of cool things that you can do, but it's completely outside of the scope of the class to go into details, especially on the latest models. The notebooks will go a bit more into details on how you implement a variational autoencoder and GANs, but no mathematical details either. And we miss a lot of other architectures and conditional generative models. But tomorrow we will see more about text generation as well. And yeah, for the lab of this part, essentially what you can do is to train a variational autoencoder to generate MNIST and written digits. And then there is also one for GAN, where you can train GAN to generate fashion MNIST images. That is essentially like the equivalent of the MNIST, but instead of numbers, you have some clothes. And yeah, that's it for this presentation. Do you have any question? Probably a lot. But. Okay, so we can go through the GAN notebook first, and then do the VA, and then I will be around tomorrow as well if you have question about the transfer learning notebook. I think someone asked before if we can reproduce the results, and this is one way of doing that. You can set the random seed, as we discussed, and I do it for PyTorch, NumPy, and also Python, just to make sure that all of them are set to a seed. And this, every time you run the notebook, will generate the same random numbers. Then what we do is always define the device to train on the GPU. And then again, we're working with images, so we always do the same transformation to load the images and normalize them. Load the fashion MNIST, which is a drop-in replacement for the MNIST dataset, slightly more complicated, but not so much. And we load the data as usual, shuffling, dropping the last batch in order to not have the last batch having a different number of elements. And then if you visualize the data set, which is always something good to do, you can see that how the instances look like. They look clothes, and you have different dresses, trousers, pullovers, and stuff like that. It's still grayscale images like MNIST, so one single channel and 28 by 28 pixels. Then for the model, this is also what I mentioned before, but essentially in this case, you have, you define two neural networks. One is the discriminator, always an instance of an N module. And then here I essentially put the recommendation on that the DC GAN paper gives, which are good recommendation to actually get good results, good looking images out of it. And essentially instead of the ReLU activation function, you use the leaky ReLU that we've seen on the first, which has a small slope in the negative numbers. You use batch normalization, and this is a particularity here. You don't use the fully connected indent layers, but you start immediately with convolutions. So you don't do the upsampling or downsampling with the fully connected layers. This is a design choice that you can do. And replace the pooling with strided convolution. So instead of using pooling, you move the kernel a bit more, not just one pixel at a time, but you move it of multiple pixels at a time, and this will reduce the size of the image. So again, you can decide to do that instead of doing the max pooling that we have seen so far. I don't remember. I think I defined this once. So this was, you didn't have to figure out all the dimension, which is a pain, honestly. And then you can do first convolution, activation, convolution, batch normalization, leaky ReLU, and you define the forward function as usual. And in the end, because we are doing, maybe I shouldn't have changed this, but I would just wanted to show you that if you're doing binary classification, you have two ways of doing it. You can have two outputs, the two classes, or you can have a single output. And the reason is that you immediately know if you have the output probability of one class, the other class will be 1 minus p. So you can essentially treat it implicitly. Is this clear? Yeah. But if you actually do two outputs, Sorry, the reason why I didn't do two outputs is because it was a bit of a pain to get like two elements with the convolutions. It would be much easier if you have the linear layer, you just set two instead of one. But in this case of the convolution, it was much easier to get a shape of one. So you get a 1 by 1 by 1 image that then you reshape into a single number. Is this clear? Okay. And then for the generator network is very similar, but in this case you have transpose convolutions that we discussed in the lecture, and essentially allows you to downsample, to upsample. So you can see as doing something similar to a convolution, but in the other direction. And so, well, we do a first upsampling. First, you increase the number of channels, but then you start decreasing the number of channels and increasing the spatial dimension. So it's the other way around of what we do for the discriminator. And again, the forward pass, you should be used to it by now. You get the single, this is something that you need to discuss. Essentially, because you're doing 2D transpose convolutions, in order to use the 2D convolutions, you need to interpret your input as something that looks like an image. And in PyTorch, an image or feature maps as channels and then spatial dimensions. But when you do the sampling from the latent space, you got a single vector. And essentially what you do in this case is that you interpret the size of Z, like the number of feature maps, and then you consider them as being 1 by 1 in size. So essentially you reshape, you have exactly the same number, but the way you interpret it is no longer a single linear vector, but you interpret it as Z size feature map of size 1 by 1, which is the same thing, but then you can apply the convolution operation to this 1 by 1 image and then make it 4 by 4, 8 by 8, 16 by 16, and finally in the last layer, 28 by 28, which is your image output. Is this clear? Do you have questions? Okay. And then finally, the tanh activation functions, because we normalize the images that we are used for training, and so they are between -1 and 1, and so the tanh activation function essentially restricts the output range between -1 and 1. That is what we want. And then, yeah, here we just test that everything works and we get the right shape out, and the shape of the output is batch size, number of channels, 1, because we are using grayscale images, and then 28 by 28 pixels. Sorry. Then you can define the loss, and this is just a convenience, because you have to define two losses, as we've seen in the class. One is called the real loss, where you always get the input from the model, but in one case, you label it as real images, so that we consider it to be the label of real images. So we set the labels in this real loss to 1, and then we compute the binary cross-entropy loss with logits, which is essentially the binary cross-entropy loss directly applied to the output of a linear layer. And again, if you add output of 2 classes, you would do as we normally do, but this is essentially the loss function for the classification, binary classification problem, where you only have one single input probability, output probability. And then for the fake loss, you do the same thing, but this time you set the labels to 0. So these are convenient functions to define essentially the labels that you want, and makes the training loop a bit clearer. Then you have the optimizers, and you have 2 of them, as I mentioned in the class. One for the discriminator and one for the generator. because you want to optimize both neural networks. So you have two neural networks, two sets of parameters. So discriminator.parameters give you the parameters of this discriminator, and g.parameters gives you the parameters of the generator, and then you can define the optimizer for each set of parameter. Then in the paper, they say that they set all the weights to a normal distribution with mean 0 and standard deviation 0.2. So we can use the weight initialization routine tricks that we've seen in the class. We define this weight initialization function, get the name of the layer, because this is what we pass in when we do the apply function of the model. And then if it's a convolution, we do we apply the weights. We sample them from a standard normal distribution. And then for the batch normalization, actually in the paper they say to set it to 0. And this one is also set to a normal distribution. And then when we do apply weight initialization, the weights are initialized with this sampling from these distributions. Then here, essentially, I do always the sampling of a fixed. So I generate a fixed batch of Z samples in order to track how the training works on this fixed sample for visualization at the end. And then, well, here's the most important part, but we put the models in training mode because we have batch normalization layers, so it's important to do that. And then in the training loop, we have, as usual, number of epochs, and then the loop over the batches. The fashion MNIST is a data set for that is labeled, so for supervised learning. But in this case, we don't care about the labels. We just care about the images. So we ignore the label. This is essentially putting the label in this variable that we discard. 0 of the gradients. So this is the usual thing that you need to remember. And then what we do is that we take one batch of real images and we pass it to the discriminator. And then we get the prediction of the discriminator. And then we compute the loss. And if you use the real loss, you will set the labels of those images to 1. So we are passing real images and labeling them as real images. Because we want to train the discriminator as a binary classifier between fake and real images. But in order to do binary classifier, we need examples from both classes, so from real images and fake images. So what we do, we also create a batch of fake images by sampling one vector in the latent space and using the generator to generate fake images. And then we pass those to the discriminator, and in this case, we label them as fake. So we use the fake loss because we generated fake images, and we want to label them as fake because we are training the discriminator, and the discriminator has to be trained to distinguish between those two classes. And so the total loss is the loss of the two batches of real and fake images, and then we can do the backward loss. Yeah.
Can you explain a bit more what goes into this summation in terms of when you calculate the backward? I guess it's not just the sum of the value, but more than this.
Yeah, I mean, you could what you can do also. This is just a shortcut, but you could put all the data, fake and real images, with the corresponding labels in one batch and just pass that to the discriminator. Because on the loss, you're doing a sum over all the examples anyway, and so it's essentially the same. It's a shortcut. Is it clear? Yeah. So actually in the lecture, I said that you can put both of them in a batch, and then with the corresponding label, and then apply the discriminator on the full batch, and then do the binary cross entropy loss essentially. Is it clear? Yeah. Okay. And then you do the backward pass that computes the gradient of this loss function, which if you look at the fake loss and real loss is just a binary cross entropy loss for the classification problem. And the real images will have labels of 1, and the fake images will have 0, labels of 0. Yeah, and then you pass. I'm thinking about your question again. I think there might be a slight complication instead, because you take the average here on the single batch, but yeah, it's very similar to doing both of them at the same time. Because here you compute the average as a reduction. I have to check exactly what you do, but maybe it's better to use sum and then divide by the number of batches total at the end. But it is essentially like a constant factor that changes. So it doesn't change the training loop. And then for the generator training, in this case, well, I mean, you did an update of the discriminator, and now you consider this discriminator as fixed, essentially. Because you are changing the weights of this discriminator with the discriminator optimizer. But then here, when we do the update of the generator, we update only the parameters of the generator. So you consider essentially, in this part, we are changing the parameters of the discriminator and leaving the generator fixed. And in the second part, we are only changing the parameters of the generator and leaving the discriminator fixed. And for the generator, we do the usual thing, zero the gradients, and then produce a batch of fake images. Well, I mean, you sample Z, and then you produce you produce the fake images. But this is essentially the interesting part, is that you pass the fake images to the discriminator that will have some predictions of whether these images are fake or real. But then when you compute the loss function, you invert the labels. So you pretend that the images were real. So if the discriminator is very good at predicting that the images were fake, by inverting the label, this loss function will be high. The only way to reduce this loss function is for the generator to become better at generating real images. And so this is where the step of the optimizer will bring the weights of the generator towards producing better images, because you inverted these labels. Is this clear? Do you have questions about this? Okay. Yeah, and then everything else is pretty much the same. You can do the evaluation here. Essentially here, I evaluate the model in the sense that I sample from the fixed Z vector that I created at the beginning in order to see what changes during the training. And this is for visualization at the end. Then, yeah, the loss function is pretty bad, but if you look at the generated images by sampling new patches and looking at the images, you can see that the images are pretty good. This oscillating loss function is a bit of a symptom of what we discussed before. First of all, it's for every iteration. It's not for every epoch, as we were visualizing before. So you expect this oscillatory behavior. And you cannot really see the discriminator. Maybe I should plot them separately. But as we discussed in the class, the GANs sometimes oscillate a bit. They have these oscillatory behaviors, and that's why they're difficult to train. But if you look at the generated images, are pretty good. And then because I saved all the images in this sample vector, you can, at different iterations of the training, you can actually go back and visualize how the images generated look like during the training. And if you do that, you can see that at the beginning, they look like rubbish, like nothing. And these strides are actually the strides of the transpose convolution, and you can see the structure. But then as you go on the training, and I use a logarithmic function here to sample a lot from the beginning and then only a few samples from the end. Because it's quite quick to start generating like somewhat reasonably looking images. And then you can see that at the end of the training, after, I don't remember how many epochs, 15 epochs, so 7,000 iterations with the batch size that we choose, you can see that you learn how to generate new images that look like the samples of the dataset. Do you have any question? No. Do you want to look at the VAE as well? Do you have time? And please feel free to leave if you have to leave at any time, and we will put the solution online. We can have a look at the variational autoencoder as well. Again, set the random seed just to not have too many surprises during during the course. And then dataset, MNIST normalization, so this should look very familiar. We can look at the images, and you can see how the handwritten digits look like in the MNIST dataset. And then for the model, this is probably slightly more complicated. Well, not probably. It's actually slightly more complicated in terms of structure than what we are used to. But I decided to use only linear layers for this one, not to complicate with convolutions. You can also try to use convolution and transpose convolution for the decoder and see if you can improve the results a little bit. The reason why, so the decoder is essentially a sequential layer that goes from the size of your latent space back to the size of one image, because we are trying to generate images. And again, the tanh activation function is the same as before. We are using it to constrain the output between -1 and 1, because this is how we normalize the images. In terms of the encoder, this time we have a slightly more difficult forward pass because we want two outputs from the encoder. And so we cannot really use a sequential model, because the sequential model just takes the output of the previous layer and pass it to the next layer. But here we want two outputs, and so we cannot use a sequential layer. So it's the first time we see this. And so we can, to simplify a bit the model, not to have everything on the forward pass, and also in order to have the decoding function available for later on, you can define sub-functions in your class, or I mean member functions of your class. And you have the encoder. And the encoder, since we are using linear layers, you get an image as an input, and you reshape it. This could be like this could be, for clarity, 1 times 28 times 28, but you reshape it into a linear vector, as we've seen before, and then you pass it to the encoder, ReLU, encoder, ReLU. And now you have this output of size hidden dimension 2. Hidden dimension 2. And now you can pass it to both the encoder that gives you the mean and then the encoders that gives you the logarithm of the variance. And then from the encoder, you can return a tuple of both numbers, tensors. And then the decoder, since we define it as a linear layer, is very easy. You just apply the decoder. And then the only thing that you need to remember is that the output is a linear layer, so you have a linear vector, and you have to reshape it into something that looks like an image. So you just use the view as usual to reshape it, and this is your output. And then for convenience, we can define the reparametrization trick function that we mentioned is what we need in order to perform backpropagation so that we don't have the sampling in our computational graph. And you can define the standard deviation as the exponential of the log variance divided by 2, because the variance is sigma squared. So you can transform it into sigma. Then you sample a tensor from a random normal distribution that has the same shape as the mean. So this underscore like means that you're sampling, so it's a new vector, but you want it of the same shape of the mean. If you want, you can also use z size in this case, because we have it, but it's just a convenience function if you want to do it generally. Yeah, because this mean also has the batch size, so you need to take that into account. And this does it automatically because you're saying sample a tensor of the same shape. And then once you have this, you can do mean plus standard deviation times this random variable, and then this is your output, what you consider your latent space vector to be. And then the forward pass, you can just encode, get the mean and the logarithm of the variance, do the reparametrization, call the reparametrization function to get z, and then decode into an image. And then this time you don't return a single tensor, but you return the output, the mean, and the log variance, because you need those to compute the loss. And so you can start to see how flexible the framework is, because you don't, like the forward function, you don't need to always output a single thing, but you can output a tuple. So it's very Pythonic. Then the loss function, apologies, there was a mistake, but it was spotted. Thank you very much for spotting it. A minus was missing, but essentially we defined the loss function. You could look at the original paper of why the loss function, they have the whole derivation there. But essentially, because these two functions are considered to be Gaussian distribution, you can compute it analytically and get this form of the loss function. And so when you have the output, input, mean, and log variance, you can compute the two terms of the loss function, the reconstruction loss, which is just the difference between output and input. And then the KL divergence, you can compute it as the sum of log variance, mean, squared, and here we have sigma squared is the variance. We have log variance, so you take the exponent and you get the variance. And then here we also weight. We add a small weight to the loss. This is again another hyperparameter of the model. But then the final loss is the reconstruction loss plus this KL divergence. And then everything else, I think, is quite standard. Again, I did this trick of generating a fixed random vector to do the sampling during the training. But then, you get the images. Again, we don't care about the labels in this case because we're not doing a classification. We're just doing a generative model, and everything else is very standard in this case. It's not like the GAN that needs very specific training loop. In this case, just zero the gradient, compute the output. This case, it doesn't return a single output, but it returns the generated image, mean, and log variance. Then you can pass all of those numbers to the loss, get the loss, compute the gradients, and then do the optimization step that will adjust the weights of the whole autoencoder. And then you can sample from the latent space, and by generating a vector distributed according to a random normal distribution, because that's what you forced your latent space to look like. And then you generate the images by using the decode function of the variation autoencoder. And then you can see the generated images, which you can definitely tell that they are numbers, which is good. And then again, if you look at what happens during training, you can see that at the beginning, the model is untrained, so it generates noise. And then as the training goes on, it starts to learn how to generate numbers by looking at many examples. And at the end of the training, you have stuff that look like handwritten digits from your original dataset.